Chapter 4, Section 2, Protein Secondary Structure. Now remember, there's layers of complexity to what we call the conformation, or the overall shape of a protein. As you go up each level, primary to secondary, secondary to tertiary, tertiary to quaternary, you go up in complexity, more and more what's going on. Primary, remember, two-dimensional structure, just a string of amino acids. Secondary here, we're going to see that 2D structure becomes three-dimensional shapes. Okay. These three-dimensional shapes are going to be determined by the individual phi-psi angles for each amino acid. Cool, because remember, point in here, here's the alpha carbon. You have those two planes coming off, one's towards the amino, one's towards the carboxyl. And they can rotate. How they rotate, that's the phi-psi angles. 0 to plus minus 180. The structures we see that will be, from the accumulative angles, the phi-psi angles from amino acid to amino acid, are going to be what are referred to as the alpha helix, the beta conformation, or you'll hear me refer to it as the beta strand, a beta turn, or just some random coil. There's no true secondary structure needed here. The alpha helix, in my mind, when I look at it and I think about it, I think of it as a corkscrew, because that's kind of what it is. As you notice right here, the gray ribbon is to signify the nitrogen, alpha carbon, carboxyl, nitrogen, alpha carbon, carboxyl. You see here with the peptide bonds, that's what's going up here. The purple balls, those are to represent whatever R group is coming off of each individual amino acids. So this ribbon is showing you what we can call the backbone of that polypeptide. This backbone wraps around an imaginary axis, okay, so just like a corkscrew does. So it's not a twist, it's a true corkscrew effect. When you go and you look at, and it's hard to see here behind my big head, if you were to take that alpha helix and you look at it end on, it is hollow in the center. All of the R groups, as you notice here, are pointed outward from the central axis. We have studied the crystal X-ray crystallography of this and the NMRs and all of this data, and we see that there is pretty much a set structure for the alpha helices. 5.4 angstroms is the distance from this point, this residue here, to a corresponding one on the next time, which means it's a full turn of the helices. Basically, it's 3.6 residues. If I wanted to be a really big a-hole, I could give you, here's a relative distance of a polypeptide, how many, of an alpha helix of secondary structure, how many turns is this, things like that. But yeah, we're not going to worry about that type of stuff. When you go and you start looking at these different secondary structures, alpha helix, beta conformation, there's a beta strand, different types of turns. What we see is there's a commonality on all the alpha helices when it comes to the phi-psi angles. Remember, phi-psi. That -57, -47. Boom. Okay. All of the amino acids that are going to associate with be part of that alpha helix are going to have that same twist, which means it's going to start putting into a curvature that just continues through all the amino acids, curves back in on itself, does a complete turn. We see the same thing with beta conformation, the beta strands. There's certain set angles, along with all the other turns and things. Now, a thing to keep in mind when it comes to conformation, to shapes, we say the helices. You know, there's a right-hand turn and there's a left-hand turn. Now it's backwards for you because you're looking at this as a camera, but this is my right hand. Take your right hand and cup it like this, okay? You cup it like that. That's what, as you see here, a right-handed helices should do. It cups around. Do it with your right hand. Yes, I know, as you look on the screen, it's the left. But for me, and my way I'm doing is my orientation, that's the right. A left-hand turn, do it with your left hand. Boom. And you notice here, it corkscrews the opposite way. Big deal, you think? They're both corkscrewing. Yeah, no, it actually does make a big deal. Because biologically, we like the right-handed helix more often than not. That's what we go with. Left-handed, a little less stable, and it's only going to show up under certain conditions and certain areas of a protein or a polypeptide where it's needed. Okay? If, 9 times out of 10 or whatever the numbers are, don't quote me on that. The majority of the times. How's that? The majority of the times when you're discussing an alpha helix or you're reading an alpha, it says an alpha helix, blah, blah, blah. It's right hand twist. Now, when you go and you look at the amino acids that are associated with the alpha helix, yes, in the right hand twist, you're going to see that what's holding them together, as these blue dashed lines illustrate, is hydrogen bonds. These hydrogen bonds, as you see there, and you see there, you see here, if you were to count from that R group around, you will see that it is 4 amino acids away. Because of the tight turn, remember 3.6 residues, that will allow this amino acid, 1, 2, 3, 4, and this amino acid in the twist, because remember it's 3.6 residues, so the fourth one, 3.6, 4, close enough, are going to be in close enough proximity that they can interact. They can hydrogen bond. Hydrogen bond, one's not strong. You start adding them up, as we see here, in just this little 2 turns of an alpha helix. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, more and more and more. That actually starts to add up. Cumulative will start to stabilize that overall structure. And you can see here, here's 1. 1 and 4 are close proximity to each other. 2 and 6, close proximity to each other. The way they're oriented, 2 is closer to 6 than 2 is to 5. Now, I'm not saying 2 and 5 can't, depending upon what's going on, else is going on around that secondary, that secondary structure, that alpha helix, maybe, but for all intents and purposes, 4 away. That's what we're looking at. We find, though, that in certain structures like the alpha helixes, there's certain amino acids that just aren't going to work well, aren't going to play well. Proline is one of them. Proline has this tendency to form a cyclic ring with itself, which is going to interfere with phi-psi angles. So, if it's there, and I'm not saying it can't be there, if it's there and it does this rigid ring thing, as you see here, this formation, our nice smooth alpha helix is going to have a kink in it, and it's going to have its overall shape distorted somewhat. Maybe it's necessary for where it's at, and maybe this is just something that's only going to happen under certain conditions, but it is something that, evolutionarily, we've tried to, the royal we living things have tried to select out for, but it still does occur. Glycine is one you're going to see quite often there because, well, it's flexible. It can form lots of bonds, or it can't form bonds. You know, it's not going to do any of these rigid structures that are going to distort, you know, an overall shape. What's interesting is when you look at carboxyl, amino terminal ends, because of what's going on here, you're going to get a relative dipole effect going on. This dipole effect. Negative charge amino acids down here at the amino. Okay, more negatives at this end means the dipole is going to be more, it's going to be more positive of what it's wanting to attract towards it. This is what this figure from the textbook, I believe, is trying to illustrate. The opposite's true with the carboxyl. When you're looking at the beta strands, an individual beta strand looks like this. You get a collection of these in close proximity. That's what you'll hear me sometimes slip up and say, the beta sheet. The beta strand, its phi-psi angles are such, and that set angle around the alpha carbon is such, that it is literally going to do this folded structure you see there. I always use the analogy when it comes to discussing beta strands back in the dark ages, when our maps were on paper and you had to fold them up, that accordion fold. If you take it, you stretch it out, and you let it relax a bit, it will take on this up-down undulation form. Beta strand. Hold on a second. Sorry, had to sneeze. So, this up-down orientation allows for the R groups to be pointed above and the R groups to be pointed below the overall strand itself. You get enough of these strands together, lay them side by side parallel, you have to take into account amino carboxyl termini. Which way are things pointing? Here's the amino, here's the carboxyl. Amino, carboxyl. Points this way, points that way, points that way. They're not one continuous, they are individual secondary structures that they're in proximity to each other, and they're just laid next to each other, either parallel or anti-parallel. Anti-parallel, you see the hydrogen bonds here are nice, back and forth. And if they're all parallel, as you know, it's hard, I can't show you behind my big head here, but look in the book, the figure in the book, you'll see it still has a hydrogen bonding pattern so that they can all stay stable. The beta turns is something we also have to take into account. So if you have your beta string running across, well, you have to bring it back around, so you can either have another beta strand form a sheet, or you can have an alpha helix or something. So 180-degree turn. I think of this as a U-turn. So I think of this as a U-turn. You're coming in. Oops, sorry. Wrong one. You are coming in from here, and you're just doing a turn, and you are exiting out that way. Excuse me. So this means you can bring, the polypeptide chain back into the center of, whether it's a globular, filamentous, whatever. It's going to be 4 residues, 4 amino acids in size. Notice the hydrogen bonding patterns, holding everything here together. Again, individually, weak, get enough of them, and it also, there's going to be some interaction of whatever this secondary structure, that secondary structure leading in, leading out, they're also going to be interacting. So it's going to be a stable turn. We see more often than not, proline is in position 2, glycine in 2, proline in 3. even though this seems to be backwards here in the figure and what I typed. Go with the figure. Glycine and proline, more often than not, are going to be associated. Something about the R group, something about the phi-psi angles they can do, means that they have a greater ability to do this. Now, those phi-psi angles, as we've seen, they're very important in what type of secondary structure can come from that short part of the polypeptide. Some very intelligent, way more intelligent than I could ever be, biochemists, back in the 60s, sat down and using technology of the day, the NMR and all this technology, were able to calculate for each amino acid the phi-psi angles coming off of that alpha helix. Remember, alpha helix, phi-psi angles. And they came up with what we refer to as a Ramachandran plot. Phi-psi, let's say phi here on the x, psi on the y. And they calculated very few psi angles are going to be in the negative. Okay. Very few phi angles are going to be positive. Yes, there are some, as you see here in this blue shaded area, but this right here, all but devoid. There may be a random one, because remember, not all polypeptide segments are going to be alpha helix, beta strand, or beta turn. There's going to be some that are just unknown or whatever. The majority are going to be here, negative phi, positive psi, or here, negative for both. Negative 60 and somewhere here in the negative 40 to, I don't know, 100-ish. In the psi, in the phi, means it's going to be a right-handed twist alpha helix. Up here in this quadrant, the second quadrant, this is where you're going to find amino acids that associate with a left-handed alpha helix. Remember, they only happen every so often in only certain conditions, which is why there's very little area associated with them. Beta sheets, parallel, anti-parallel. And here in this little bean-shaped area, this is where the right twist beta sheets. Yes, even the beta sheets, you get them laid down next to each other, they can form a twisted sheet. It's not always going to be that up-down map formation. Excuse me, I got a tickle on my throat. You take some polypeptide. I don't remember what they said this polypeptide was, and they say it in the figure legend in the textbook. And they went amino acid by amino acid. And you see quite a few fall down here, which, if you remember, are right-handed helix. Up here in the beta strands, parallel, anti-parallel, the one with the twist. Does this completely tell us everything about the shape, the native conformation of this polypeptide, this protein? No. It just tells us there's going to be a lot of alpha helices and some beta strands, maybe forming sheets. There are exceptions to the rule. Glycine, we've seen glycine pop up a few times in this lecture on different areas. Glycine seems to be the other. Doesn't fall under all of our rules quite well. These secondary structures, we want to be able to study them. We want to be able to discuss them in other ways, figure out what it is about that structure that instills so much stability in the polypeptide. One of the ways we have of measuring, of detailing these structures is what is referred to, as you see here, as circular dichroism spectroscopy, blah, blah, blah. Turns out the peptide bond is a bit of a chromophore, okay? It interacts with wavelengths of light. And when you put the not the the complete polypeptide, or at least segments of it, I think this is going to be some form of a secondary structure. You put it in, you can see at certain wavelengths, alpha helix, beta conformation, beta strands will light up. The unstructured, because remember, not everything's going to fall in an alpha helix, beta strand. Well, all those others, they also have absorption spectra that is different than what we see with alpha helix or beta conformation. Notice here the wavelengths. This is well below anything we could do with a spec. So don't think we're going to be doing this here. This is going to be more infrared.